Very good morning, dear students. Welcome back to my video lecture series. This is your network analysis subject in which we are going to study network theorems. So far we have studied superposition theorem and Thevenin's theorem. We have seen the statement, we have seen the procedure, the application, the limitation and advantages of superposition theorem and Thevenin's theorem respectively in my previous video lectures. Now today we are going to learn and understand Norton's theorem. Norton's theorem is actually a dual concept of the Thevenin's theorem. That is why it is advisable to understand very clearly the working and the statement of and the application of Thevenin's theorem. Once you are able to understand and practice good questions over Thevenin's theorem, the Norton's theorem will become very much easier to handle, very much easier to understand and very much easier to go with any kind of problems coming under Norton's theorem. So let us start Norton's theorem. This is your statement. The first part is actually statement. Statement is actually very important whenever you are facing any kind of interaction with electrical faculty or electrical interview board. They may at first ask the statement of any theorem. Why statement is important? Statement is important because it has some vital information. What information it is going to give you, I am going to tell you. See this, the statement of Norton's theorem. See this. Any linear, it means what? The circuit should be linear. Let me first dictate it for you. Any linear, active, bilateral, complicated network across its load terminals can be replaced by single current source and one parallel impedance. This is your complicated network, and it should be linear, active, bilateral. Okay. Complicated means it is having lots of elements, lots of sources, but it should have linear, active and bilateral network or elements inside this bigger or complicated network. Then only we will be able to apply and go for Norton's theorem application. Now understand clearly what Theorem was doing for us. It was actually simplifying the bigger network, complicated network. In the same manner, Norton's theorem is actually simplifying a complicated network, but that complicated network should have linear, active, bilateral components within it. Otherwise, we'll face lots of problem or will not be applying those theorems. Either it is your Thevenin's theorem or either it is your Norton's theorem. So, this is a network, any linear, active, bilateral, complicated network, and across its load terminals. Where is the load terminals? This is your load terminals. AB can be replaced by a single current source. This is your single current source IN, and one parallel impedance. This Zn is in parallel with this single current source. Now, see this. IN is equal to Norton's equivalent current. IN is your Norton's equivalent current. This IN is your Norton's equivalent current. And this is the short circuit current. Please mark it. This is the short circuit current. In Thevenin theorem, we were opening the terminals and we were searching for open circuit voltage. That was Thevenin voltage. Here we are short circuiting the terminals and we are finding short circuit current, and we are finding here short circuit current. Please mark it. Which is passing through terminals AB. When short circuited. when it is short circuited, it is passing through the terminal. It is passing through the terminal A and B. Well, we'll see in the next slide when it is actually how it is working. Now the Zn is Norton's equivalent impedance. Norton's equivalent impedance. It is actually analogous to ZTH. What is this? ZTH is driving point impedance at terminals AB. When all the independent sources are replaced by their internal impedances. Okay, this is also called ZTH, which is your driving point impedance at terminals AB when all the independent sources, please mark it, when all the independent sources are replaced by their internal resistances or impedances. Please mark this word, all the independent sources. We are not talking here about the dependent sources. Okay, I will give you key idea and working procedure to solve numericals when it is having dependent sources in my upcoming video lectures. But the theorem is having this statement only, and we have to go with the theorem's original statement. We'll add later on the exceptions present while solving numerous numerical examples. The procedure, that is a way of working with, way of applying with your Norton's equivalent theorems, Norton's equivalent circuit. This is your Norton's equivalent circuit. From where it has come? It has come from Norton's theorem. We have applied Norton's theorem. What is the process to application or the applying Norton's theorem? First, we have to remove the load. What we were doing in Thevenin's theorem, it is very much similar to in Norton's theorem. You may remember that in Thevenin's theorem, where the response was asked, there was an element across which a response was asked, and while applying that Thevenin's theorem, we were first of all removing that element from the original circuit, whether it was linear or non-linear. Non-linear elements were considered as load. You must be remembering there. Okay. So here we are also removing the load, if any. See this? In this diagram, the load has been removed. So this has been removed. It is opened. It is opened. Let me show it. This is opened. This is opened. You may be saying this. Okay. Now, the first point was removing the load across the terminals if there is any present. The second point is, let me write it for you. First point was removing load. Load was removed. Let me remove. It was removed. Okay. And the second point was, while doing your Norton's theorem, while applying your Norton's theorem, that is coming under procedure, short circuit the load terminal AB. This was present across A and B. Okay, this was present across node A and B, terminal A and B. Okay, so in second point, what we are doing? We are going to short circuit this terminal A and B. We are short circuiting this terminal A and B, and we are calculating short circuit current passing through it, that is that is IN, that is we are going to calculate IN, the short circuit current passing through terminal A and B. We have short circuited this. Point number 3, that is while calculating Zn, which is equivalent, Norton's equivalent impedance, while calculating or while having Norton's equivalent impedance, please replace all the independent sources. That is, we are going to replace all independent sources present by their internal impedances, and find the driving point impedance as seen from load terminal AB. This was your load terminal A, this is your load terminal B, this is your network. Okay, this is your network. So we are seeing the circuit from here. Assume yourself you are standing here, and you are seeing circuit from here. Okay, you are seeing circuit from here. So how circuit will behave electrically when you are seeing from this side? Okay, this is Zn and equal to Zth. We have studied just now, just before this slide. That Zn is actually your Zth, which is your driving point impedance, which seen from the load terminal AB. I have given you are standing here. Okay, just assume you are standing here and you are seeing the network from here. Okay. See this? We are back to our original circuit. We have studied how it is actually Zn and Zth related. Now draw the Norton's equivalent circuit. Now we are drawing the Norton's equivalent circuit. This is your Norton's equivalent circuit. What we are doing, we are actually going to connect that removed ZL. We are going to actually connect that removed ZL back into the equivalent circuit where we have found out IN and ZL. See this, where we have found out the IN and Zn. Now the circuit is, see this, this circuit is now see this. This is your IL current. Now we have to find IL current. Now IL load current is equal to this is your current source. Okay. Now what we are going to do? We are going to apply current division rule. This is in parallel with this IN, and this is also in parallel with this IN. So I load current is flowing across this ZL. So we are going to find out IL. IL is equal to, first we have to write the total current of the circuit, that is IL into the resistor or the impedance in neighborhood of the branch through which IL is flowing. Just remember, just see this. Okay, about the total impedance of the parallel paths Zn plus ZL.